This call is now being recorded.
Okay, this afternoon I'm going to continue my discussion. We are now on section 2 of chapter 4. We have conditional distributions and independence. Okay, so we have here the basic definition. Let xy be a discrete bivariate random vector with joint PMF, f of xy, and the marginal PMFs f sub big X and then f sub big Y. So for any x such that the probability that our random variable is equal to the realized value small x will be equal to small f sub big X of evaluated at x. Uh, this is an assumption that it's positive. Then the conditional probability mass function of y given that x is equal to the realized value small x is a function of y, and this is being denoted by this symbol. Okay, so if you want to emphasize the random variables x and y, you can have this notation for the conditional PMF of y given x. Pwede we have this some notation. Okay, so it is defined as this conditional PMF of y given x, which is a function of y. This is equal to this fractional expression in which the numerator is the joint PMF of x and y over the marginal PMF of the random variable x. Take note, we have assumed that the marginal PMF of x is positive. And then for any such, for any y such that the marginal PMF of y is positive, the conditional PMF of x given that y is equal to the realized value small y is a function of x. It's being denoted by this symbol, and it is defined as, so you can have this symbol f of x given y, or the probability that our random variable x is equal to small x given that y is equal to small y, and it is equal to this fractional expression in which the numerator is the joint PMF over the marginal PMF of y. Okay, since we have called this small f of y given x a probability mass function, then we're going to verify that indeed this function is a probability mass function. Okay, so first we're going to check if the PMF, or it's the function f of x, f of y given x to be non-negative for every y. And then this is non-negative for every y. It's because the joint PMF of x and y is non-negative. At the same time, our marginal distribution, our marginal PMF of x is positive. So the uh, conditional PMF of y given x is non-negative for every y. Then secondly, we're going to show that the countable sum of these PMFs evaluated on y, the summation is over all y, will sum to 1. And then by definition of the uh, conditional PMF of y given x, we have here the summation of the sum, rather the summation of the joint PMF over the marginal. And then since we know that the joint PMF is the joint PMF is indeed a PMF, so that is just equal to, or the sum of this joint PMF will be equal to the marginal PMF of x. So it is equal to 1. So clearly, our conditional distribution of y given x is indeed a probability mass function. And let's have an example to illustrate this definition. Calculating conditional probabilities. Say we're going to define a joint PMF of this random vector of x and y by, so we have the joint f of 0, 10 is equal to f of 0, 20, and that is equal to 2 over 18. Then f of 1, 0 is equal to f of 130 equals to 3 over 18. Then f of 120 is equal to 4 over 18, and then f of 230, 2 and 30 will be equal to 4 over 13. Okay, so our goal here is to find the conditional distribution of y given x. So if you want to find this function, then we need to find our marginal PMF of x. So for our random variable x, if we're going to look the defined joint PMF, the possible values of this random variable x, we have 0, 1, and 2. So we have here 0, then 1, then we have, lastly, we have 2. Okay, so first we're going to compute for the marginal PMF of x. Say this marginal PMF of x, f of sub x evaluated at 0. So we have here, so we're going to fix, no? We're going to fix our x at 0, and then we vary along the y values. So we have this joint PMF, f of 0, 10, and then f of 0, 20. So this is actually equal to 2 over 18, and this is also equal to 2 over 18. So the sum is equal to 4 over 18. And then when x is equal to 1, then the marginal PMF of x, so we have this sum of the joint PMF, f of 110, f of 120, f of 130. So we have here 3 over 18, and then this is also 4 over 18, and then this one is 3 over 18. So that is equal to 10 over 18. And then for the last value of x, which is 2, we have this marginal PMF of x evaluated at 2. So f of 230, and that is equal to 4 over 18. So for x is equal to 0, this joint PMF f of 0y is positive only when the value of y is equal to 10 and 20. Thus, the conditional PMF of y given that x is equal to 0, okay, x is equal to 0 is positive only for y equals 10 as well as y is equal to 20. So if we're going to compute for the conditional PMF of y, no, y is equal to 10 given that x is equal to 0. So we can express this, no? The probability that our random variable y here is equal to 10 given that our random variable x here is equal to 0. Okay, so according to our definition, we have the joint over the marginal. So we have already computed for the marginal PMF of x evaluated at 0, that is 4 over 18. And then we have this value given, 2 over 18 for our joint. So the answer is equal to 1/2. And then for the conditional PMF of y is equal to 20, given that x is equal to 0, clearly, by substituting the values of these functions, we have 1/2. Okay, for x is equal to 1, the conditional PMF of y, given that x is equal to 1, is positive for these values of y, 10, 20, and 30. Okay, so to compute for this conditional PMF of y is equal to 10, given that x is equal to 1, that is also equal to the conditional PMF of y is equal to 30, given that x is equal to 1. Okay, by substituting the values of this, so here this is the either the joint, no? The joint, we have here 1, 10, and that is equal to 1, 30. And given in the problem, this is equal to 3 over 80. While in our denominator, this is the marginal EMF of x evaluated at 1, which is equal to 10 over 80. Okay, simplifying our fraction or complex fraction, then the answer is equal to 3 over 10. And similarly also, if we're going to compute for the conditional PMF of y is equal to 20, given that x is equal to 1, say here, the answer is equal to 4 over 10. Then lastly, for x is equal to 2, we have this answer, which is equal to 1. Okay, since we have already computed for the conditional PMF of y given x, then we can use this conditional PMF to compute other probabilities. May na siguro yung mga examples na yan. Okay, so other conditional probabilities can be computed using this conditional PMF. For example, we have here, we're going to determine the probability that y is greater than 10 given that x is equal to 1. Okay, since the possible values of y here, we have 10, 20, and 30, but we restrict that y should be greater than 10. So we consider only values of y, which is 20 and 30, conditioned that x is equal to 1. Okay, so we have already computed this conditional PMF. This is equal to 4 over 10. Okay, and then the other one, 30. Okay, we have 3 over 10 above. Okay, so we have 7 over 10. And then the probability that y is greater than 10, given that x is equal to 0, okay, since the PMF is only positive when we have y to be equal to 20, given that x is equal to 0. Hence, we have this conditional PMF of 20 given 0, and the answer is equal to 1/2. Okay, for the continuous counterpart, we let xy be a continuous bivariate random vector with joint PDF f of xy, and then marginal PDFs, small f sub big X evaluated at x, then small f sub big Y evaluated at y, and then for any x such that the marginal PDF of x is positive, then the conditional PDF of y given that x is equal to x. Still, we use this notation for that. And it is equal to the joint PDF over the marginal PDF of x. Then for any y such that the marginal PDF of y is positive, then the conditional PDF of x, given that y is equal to small y, is a function of x. Okay, this is a function of x denoted by, okay, we have this notation, and it is equal to this fractional expression in which the numerator is the joint PDF of x and y over the marginal PDF of y. Okay, as I have said, we have some usefulness of these probabilities as well as the conditional PDFs. If we have g as a function of y, since we know it's a function of a random variable y, g of y is also a random variable. And so we can have this conditional expected value of g of y, okay? The conditional expected value of g of y given that x is equal to the realized value x. It's given by, so for the discrete case, we have here the countable summation of g of y, g of small y, times the conditional probability mass function of y given x. And the sum is over all values of our, or the mass points of our random variable y. And then the conditional expectation of g of y given x in the continuous case, then we have here the improper integral of g of y times, okay, the conditional PDF of y given x. Then this is a dy, okay, uh, evaluated from negative infinity to positive infinity. Okay, so the conditional expected value has all of the properties of the usual expected value listed in theorem 2.2.5. So yung mga properties natin, when we have the only a random variable, for the expectation can also be applied for this conditional expected value. Okay, so moreover, the conditional expectation of y given x provides the best guess at y based on the knowledge of x. Let's have an example. Okay, calculating conditional PDFs. So as an example, 4.1.12, let the continuous random vector xy, we have already computed this last meeting. Okay, we have here the joint PDF of x and y. It is equal to e to the negative y. And then given that x is greater than 0, but x is less than y, and y is less than infinity. Okay, suppose we wish to compute the conditional PDF of y given x. So the goal here, we're going to find this, no? The conditional PMF of y given x. Okay, so based on our definition, we need to compute first for our marginal, no? The marginal PDF of x. Okay, so we have here the marginal PDF of x is computed as follows. If x is less than or equal to 0, in other words, x is non-positive, then the joint PDF will be equal to 0. Okay, based on our condition, x here should be positive. So if it is non-positive, then the joint will be equal to 0 for all values of y. And so the marginal PDF of x will be equal to 0. But if x is equal to 0, then our joint PDF will be positive only if, because of the condition that y is greater than x here, or when x is less than y. Pwede naman ganun. Okay, so, or we can write it using the piecewise function. We can have this joint PDF. Okay, it is equal to 0 if we x to be non-positive. And then it is equal to e to the negative y if okay. So using our formula for the marginal PDF of x, we have here the improper integral of our joint PDF dy evaluated from negative infinity to positive infinity. Since we're going to evaluate this integral with respect to y, and then y is greater than x, hence if we're going to apply the indicator function, then the bound below for our integral would be x to positive infinity. So if we're going to solve this, using calculus, you can express this as limit as b. Ano na ito, no? Hindi na lang nakibutang. So we have the limit of the integral. We have here x to b at e to the negative y dy, and b approaches to positive infinity. And then if we're going to evaluate this integral, the integral natin, e to the negative y dy, evaluated x to b, we have here the negative of e to the negative y, x to b. So we have here negative e to the negative y minus minus, so we have plus e to the negative b pala, sorry. E to the negative b plus e to the negative x. So if we're going to apply this, this is not equal to the limit, the negative e to the negative x, and then minus e to the negative b as b approaches to positive infinity. Okay, e to the negative b is the same as 1 over e to the b, and then if we're going to apply now the limit, 1 over e to the positive infinity would be equal to 0, so the answer would be equal to e to the negative x. So that's our marginal PDF of x. Thus, x has an exponential distribution. Okay? X has an exponential distribution. The scale parameter of this exponential distribution is equal to beta, which is equal to 1. Okay, 1. So from definition 4.2.3, the conditional distribution of y given x can be computed for any positive x. Since the marginal PDF of x is positive for x greater than 0. So here, this is what our goal. We have the conditional distribution of y given x equal to this. Then we have here our joint PDF over our marginal, and we have this. Okay, it's very clear. We have the expectation of e to the negative y minus x. Again, the conditional distribution of y given x is also an exponential distribution. Then this is for y greater than x, and then here for y less than or equal to x is equal to 0. Okay, so it's an exponential distribution. And then we consider x here is as our location parameter. I have discussed this in the last part of chapter 3. X is the location parameter, and the scale parameter here, we denote it by beta, and that is equal to 1. Okay. So the conditional so if we're going to we have already the conditional PDF, the conditional PDF of y given x. Then we can now compute for the conditional expectation of y given x. Okay, so here, supposedly we have here negative infinity to positive infinity. Then we have y times the conditional PDF of y given x. We have e to the negative y minus x quantity. And then we have this dy. And then okay, We are evaluating this integral with respect to y, and y is greater than x. Okay, so we have that. And then we're going to use the integration by parts here. Integration by parts. Evaluate this in proper integral. I will be able to get this 1 plus x. I tried it, and then I checked that the answer is indeed 1 plus x. Okay, so we have already computed for the conditional expectation of y given x. We can also compute for the variance of the probability distribution described by this conditional probability density function. So the conditional variance of y given x, this is our notation. Okay, so uh, using the ordinary definition of the variance applied to this conditional variance, so we have the variance, conditional variance of y given x would be equal to the conditional expectation of y squared given x minus the square of the conditional expectation of y given x. Kasi yung ordinary definition of the variance, say we have y, we have the expectation of y squared minus the square, okay, of the mean of y. So applying this to our example, if we're going to compute for the conditional variance of y given x, hence we have the, okay, that's by definition of the expectation, yung first term natin, this is by definition. And then for the second term here, it's also by definition, but this is equal to 1 plus x quantity square, okay? Because we have the value for the conditional expectation of y given x. Okay, so then we have that. Okay, so if you're going to evaluate this, the answer is equal to 1. So in other words, we have the conditional variance of y given x to be a constant, not a function. No? In this case, the conditional variance of y given x is the same for all values of x. Okay, in other situations, however, it may be different for different values of x if it's not equal to a constant which is equal to 1. Okay, so this conditional variance might be compared with the unconditional variance of y. The marginal distribution of y is gamma 2, 1. And then we can see that for this distribution, the variance of y will be equal to 2. So if we're going to recall, for the gamma, yung gamma na sabihin na natin y here has a gamma distribution, alpha, beta. But in this case, alpha is equal to 2, beta is equal to 1. The PDF of y here is equal to 1 over gamma of 2. And then we have here 1 to the y. Sorry. Isa na to. 1 over gamma of alpha, beta of alpha, and then we have here y of alpha, 2 minus 1, and then e to the negative y over beta. So y here is positive. And then if we're going to compute for the mean of this, so the mean of y is equal to alpha beta, so 2 times 1. And then the variance of y, the unconditional, no, this is the unconditional variance of y here we have alpha, we have 2, then times a 1 square, beta square. And the answer is equal to. Okay? So now given the knowledge that x is equal to x, the variability of y is considerably reduced because in the conditional variance of y given our x, the variance is equal to 1. Okay. By the way, in the previous examples that we have, the conditional distribution of y given x was different for different values of x. But there are some situations that knowledge of x does not give us any information about y, and this implies that the relationship between x and y is independent. Now we have this independent relationship. So let's have this definition. Let xy be a bivariate random vector with joint PDF or PMF, f of xy. Then we have the marginal PDF or PMF, f sub x, f sub y. Then x and y are called independent random variables if for every real number x and every real number y, the joint PDF or PMF of xy will be equal to the product of the marginal PDF of x and the marginal PDF of y. Yeah. Take note, this is true for every real number x and y. If this equality holds only for some real number x and y, we cannot conclude that x and y are independent random variables. Must satisfy, the equality must satisfy for every real number x and y. Okay, so we have here, if x and y are independent, then the conditional PDF of y given x, this is by definition the first equality, and then applying the definition for independence, the joint is equal to the product of the marginals, then this would cancel, and it is equal to the marginal distribution of y. So another implication, say x and y are independent, if the conditional of y given x is equal to the marginal PDF or PMF of y, regardless of the value of x, then we have x and y to be independent. Okay, thus for any a which is a subset of R, and then x is a real number, the probability that y is an element of a given x will be equal to this. We have here the integral of the conditional PDF of y given x dy, and that will be evaluated on this subset A of R. Okay, since the conditional, since x and y are independent, the conditional PDF of y given x will just be equal to the marginal PDF of y. And this will be equal to the probability of y to be an element of A. So the knowledge that x equal to this realized value x gives us no additional information about y. Okay. So for definition 4.25, there are two applications. One, we can check whether x and y are independent if we can show that the joint PDF is equal to the product of the marginal PDF for all real values x and y. Okay, it should be true for all real value x and y. And then another use of that definition, say if we're going to define a model in which x and y are independent, then consideration of what x and y represent might indicate that the knowledge of x should give us no information about y. So in this case, we should specify the marginal distribution of x and y and then define the joint distribution as the product given in 4.2.1. So let's have an example. Okay, checking independence. Okay, consider the discrete bivariate random vector x and y with joint PMF given by this. F of 10, 1 is equal to f of 21, f of 22 equal to 1 over 10, f of 10, 2, f of 10, 3 equal to 1/5, and f of 23 is equal to 3 over 10. So if we're going to compute for the marginal PMFs, since this is a discrete case, we have the possible values of x here. We have 10 and 20. No, we have two possible values of x. So if we're going to compute for the marginal PMF of x evaluated at 10, that will also equal to the marginal PMF of x evaluated at 20. Okay, so the answer there is equal to 1/2. Pwede naman siguro natin i-evaluate. We fix our x at 10. No? We fix our x at 10. So we have here the countable summation. F of, say, ano yung unang 10? Say 10, 1. And then we have f of 10, 2. Then we vary along y. On the y values, okay, 10, 3. So we have here 1 over 10. And 10, 2, that is 1 over 5. That is actually 2 over 10. Okay, 2 over 10 pa rin yan siya, no? And then 10, 3. 1/5. That's 2 over 10. 2 over 10. Ang second term at saka third term, 2 over 10. So meron tayong 4 over 10 plus 1 over 10. That's 5 over 10. And the answer is equal to 1/2. Okay? Then similarly, you can compute also for the marginal PMFs of y. So when the realized value is 1, okay, we have here 1/5. Verify. Itong part na lang muna isa. So we fixed our y at 1 and then we vary along the x. So 10, 1, f 21. So this is equal to 1 over 10 plus 1 over 10 is equal to 2 over 10. And this is equal to 1 over 5. So we have that. And then you can verify for the other PMFs. Okay, we have already computed for the marginal PMF of x as well as the marginal PMF of y. Okay, let us now check if x and y are independent. So take note, it should be the joint should be equal to the product of the marginal for all. Okay, this for all real values x and y. Okay, so we have here, say if we have x is equal to 10 and then y is equal to 3, the joint is equal to 1/5, no? Given in the problem. So joint 1/5, and then the f of 10, this one, the f of x, the marginal evaluated at 10 is equal to 1/2, and then of y given 3 here, the answer is also equal to 1/2. And then we have shown here that the joint PMF is not equal to the marginal the product of the marginal PMF of X and Y. Okay, so by this example, this implies that X and Y are not independent. Though we know that for some values of X and Y, the joint is equal to the product, such as this. When we take X here to be equal to 10 and then Y is equal to 1, and then we have shown that the joint is equal to the product of the marginal. But it must be true for all or for every X and Y. Okay, so we have here the verification of X and Y are independent by direct use of the equation 4.2.1 would require the knowledge of the marginal distribution of X as well as the marginal distribution of Y. Okay, another lemma that would show again that the random variable X and Y are independent. We have here in lemma 4.2.7 that the joint PMF or PDF is equal to the product of two functions, g of x and h of y, where g of x here is a function of x only, and then h of y is also a function of y only. Says here, let x and y be a bivariate random vector with joint PDF or PMF, f of xy, then x and y are independent random variables if and only if there exist functions g of x and h of y such that for every real number x and real number y, the joint, sabihin na natin PDF na yung gagamitin ko, the joint PDF will be equal to the product of these two functions. Okay, as I've said, g of x is a function of x only, and h of y is also a function of y only. Okay, we have here in our lemma a biconditional statement. That is, P implies if and only if Q. So that means P implies Q and Q implies P. So the P implies Q, that's actually the only if part, and the Q implies P if is the if part. So to prove this lemma, the only if part is quite trivial. Now, the P implies Q. When you say P implies Q, we're going to assume that our x and y are independent random variables. And then we're going to show that the joint of x and y will be equal to the product of these two functions. Okay? Since x and y are independent, so if part natin, x and y are independent, we have equal, this is equal to the product of the marginals. Okay? And then, okay, so if we're going to define g of x is equal to the marginal PDF of x, and then we're going to define h of y to be the marginal PDF of y, then we have proved the only if part. Okay. Next, to prove the if part for a continuous random variables, we're going to assume the Q, the Q statement. That is, if the joint PDF of xy is equal to the product of these two functions, g of x and h of y. Okay, excuse me. And then we define, okay, so we define this improper integral. The improper integral of g of x dx evaluated from negative infinity to positive infinity be equal to c, and then the improper integral of h of y dy evaluated from negative infinity to positive infinity be equal to d. Okay, we have that. And then where c and d are constants, Okay, so satisfy. Satisfy this equality. So if you take C, D equal to this, and then using the property of integral, okay, we can write it into we can write it this the product of the integral to be this double integral of g of x, h of y, dx dy. And then since we have assumed that the product is equal to this, then we have that. And we know that our f of xy is a joint PDF. Therefore, this double integral of the joint PDF will be equal to 1. So the product CD is equal to 1. Okay, next we're going to compute now for our marginal PDFs. Okay, so the marginal PDF of x. Okay, the marginal PDF of x I have here. We have this improper integral of g of x, then h of y dy. Okay? Take note, this is by definition. Itong first equality, this is by definition of the marginal PDF. Okay, by definition. Then this is actually equal to, we can write the factor that does not depend on y before the integral sign. So we have here h of y dy. And that is equal to d. Itong part na to is equal to d. So we have g of x times d. Then similarly for the marginal PDF of y, again, this is by definition. Then we can write the factor that does not depend on x before the integral sign. And then the remaining expression in our integral is equal to c. Okay, so we have that. Now, using 4.2.2 as well as 4.2.3, we have here our joint PDF. Okay, our joint PDF. By assumption, equal to this product. And then since CD is equal to 1, equality is preserved. And then if we're going to group, okay, say we have this, D, and then we have h of y times c. And then using 4.2.3, the joint is indeed equal to the product of the marginal PDFs of x and y. Okay, showing now that our x and y are independent. For the discrete case, we're going to replace the integrals with sums. Okay, so the proof is for the continuous case, madam. But you can show also the proof in the discrete case. Okay, another example. By the way, any questions or clarifications? No questions? Okay, so let us proceed. Consider the joint PDF. Okay, we have here, this is our joint PDF. X to be positive and then Y to be positive. If we define g of x, in this case, it is equal to x squared e to the negative x over 2 when x is positive, and then 0 if x is less than or equal to 0, or non-positive. And then h of y equal to this. Okay, it's being expressed in a piecewise manner. Then according to our lemma, the joint, if the joint can be expressed as the product of two functions, okay, not necessarily ito yung ating marginal PDF of x and y. If you can express the joint to be the product of two functions, g of x and h of y, for all x, for all real number x and y, then we can conclude that x and y are independent random variables. So no need to compute for the marginal PDF. Pwede naman yun ma-check, no? Okay, let's proceed to theorem 4.2.10. Okay, let x and y be independent random variables. By the way, this theorem is very important. We're going to use this when we this can be applied especially in determining the marginal, rather the moment generating function of a random variable. If we have two random variables, x and y. Okay, so let x and y be independent random variables. Then for any subset A of R, B a subset of R, the probability that x is an element of A, and the probability that y is an element of B equal to the product of this probability, to the probability that x is an element of A. That is, take note that we have these events. The event that x is an element of A and the event that y is an element of B are independent events. So if we can show that this probability is equal to the product of this probability, then we have independent events. And then for B, let g of x be a function only of x and h of y a function only of y, then the expectation of the product of these functions g of x and h of y will be equal to the product of the expectation of g of x and the expectation of h of y. So we're going to prove this for the continuous case. Okay, let's proceed. For the continuous case, the expectation of the product g of x, h of y, by definition, okay, we have here g of small x, g of small y, and then the joint probability density function, dx dy, evaluated from negative infinity to positive infinity. Okay, and then since we know that x and y are independent, okay, we assume that nasa taas yan, no? X and y are independent. So the joint is equal to the product of the marginals. Okay, since g of x is a function of only x as well as f of y is a function of only y, then using the property of integral, then we can have this product of two integrals. And then, okay, we have that. So commutative naman ito, part na to. Well, we can have now the product of these two integrals. And by definition, again, it is equal to the expectation of g of x and the expectation of g of y. So you see that now we have shown that the expectation of the product of g of x and h of y is equal to the product of the expectation of g of x and then expectation of h of y. Okay, so to prove part A, says here the result for discrete random variables is proved by replacing integrals by sum. Okay, and then for part A, you can prove it by a series of steps similar to the steps that we have used above. But we have another way of proving part A. So for part A, say we let g of x be an indicator function of set A. So when say indicator function of set A, we can have g of x here to be equal to the indicator function of x on set A. And this is equal to 1 if x here is an element of A, and then 0 otherwise. X is not an element of A. And then we have also h of y be an indicator function of set B. So we have here h of y. It's an indicator function of on set B. Again, this is equal to 1 if y is an element of A, then 0 y is not not A, B. And then we have also the product g of x, h of y is an indicator function of a set C, which is a subset of the Cartesian plane, R squared, where we define C here to be the set of all ordered pair xy, okay? Ordered pair xy such that x is an element of A, and then x is an element of y. Somehow, itong set C para yung Cartesian product of these two sets, A and B. We have here set C. Okay, so we have here a note telling us that the mean of g of x is equal to the probability that x is an element of A. So the implication dito, no, meron tayong implication that we have a note here. The mean of g of x here would be equal to the probability that x is an element of A. And then here, we have the mean of h of y. Random variable yan siya ng y, no? It's the probability that y is an element of B. Take note of this, no? Indicator function, which is the product g of x and then h of y. Okay, so the probability that x is an element of A and y is an element of B, take note of that. According to our definition, we have here the probability that xy is an element of C. From here, x is an element of A, y is an element of B. So this ordered pair of random variables should be an element of C. Okay, we have that. And then by this note, itong note natin to, by this note, parang pareho dito, by this note, then the probability of xy, an element of C, will be equal to, parang pabaliktad, no? Pabaliktad, ganun yung steps natin. Will be equal to the expectation of the product g of x and h of y. And then since we have independent random variables here as assumed in our theorem. So the function of x as well as the function of y are also independent. Hence, we have now the product of the expectation of g of x and then the expectation of g of y. Again, using this note, yung asterisk star natin dito, then we have shown the product of the probability that x is an element of A and the probability that y is an element of B. Okay, so this is the proof of part A. Part A. Okay, so let's have an example. 4.2.11, expectations of independent variables. Here, we let x and y be independent exponential 1 random variables. So in this case, the x and y are standard PDF. Okay, does not depend on any parameter. So we have here a beta constant is equal to 1. Okay, so from theorem 4.2.10, if we're going to compute for the probability that x is greater than or equal to 4, then y is less than 3, according to our theorem, it will be equal to the product of the probability that x is greater than or equal to 4, and then y, probability that y is less than 3. Okay, so in general, if we're going to consider the exponential beta function, lagay na lang natin dito. Okay, say for example, if x here has an exponential, ito, and then our x here is a negative.
When it's time to ride,
So if we're going to determine its CDF, the cumulative distribution function of this distribution,
when it's time to fly.
having this exponential
Me and my
distribution,
brother, we stick
is equal to
together,
the
no other. We
probability that
blowing
x
up
is less
like a
than
bubble, and we
x. And you can compute this. Pwede naman yan, the integral from negative infinity to x. And then you use your PDF, U, then you have your D. And you can verify that the CDF for this is equal to 1 minus e to the negative x. Okay? So for the probability, itong probability, so the probability that y is less than 3 here. It's less than 3. Uh, by the way, if we have a continuous case, the non-strict as well as the strict inequality, their probability value will just be the same. So this is just the same as the probability that y is equal to 3. And then using our, this is the CDF, and that is equal to 1 minus e to the negative 3. Okay, so we have the results. While for the probability that x is greater than or equal to 4, okay, the probability that x is greater than or equal to 4, okay, this is equal to 1 minus the probability that x is less than 4. Again, we have a continuous random variable here. Pareho lang naman yan, no? So we have here 1 minus, okay, we have 1 minus e to the negative 4. So the answer for that would be equal to e to the negative 4. Okay, so we have applied now our theorem to compute for this probability. And then if you let g of x be equal to x squared and then h of y to be equal to y, we see that the expectation of the product of the of this random variable x, y, y, then we have assumed that x and y are independent. So it will be equal to the product of the expectation of x squared and then the expectation of y. And then expectation of x squared, that's actually a term for the variance, no? Then we can express it in this form. And then the expectation of y. And then if we have the an exponential distribution, no? Kung meron ka, ang mean nito, ang mean ng x will be equal to the parameter beta. And then the variance of this is equal to the square of our parameter beta. Kaya ito, 1 naman yung beta natin dito because we have a standard PDF, exponential PDF. Does not depend on any parameter. No, we have walang beta dyan. So 1, constant. So the mean of x here is equal to 1. The variance of x is also equal to 1. Same with the mean and the variance of y equal to 1. Okay, so therefore, this is equal to 1 plus 1 squared. Then the mean of y is 1. And the answer is equal to 2. Okay, so this is an example illustrating our theorem 4.2.10. Okay, hindi pa naman time. Let's continue. So the following result concerning sums of independent random variables is a simple consequence of Theorem 4.2.10. So nakita niyo ang application ng Theorem 4.2.10. We have here in Theorem 4.2.12. So let x and y be independent random variables with moment generating function, big M sa big X evaluated at t, big M sa big Y evaluated then the moment generating function of the random variable z, in which we have expressed z as the sum of x and y. Then the moment generating function of z evaluated at t will just be equal to the the product of the moment generating function of x and the moment generating function of y, both evaluated at t. So the proof is so short. Okay, so this is by definition, yung first equality, no? That's by definition. And then by substitution, yung second equality, z is equal to x plus y. And then for this equality, using the property of the exponential function. And then since we know that x and y are independent, it also implies that the function, no? The function of x and the function of y are also independent. Hence, we have here the product of the expectation of e to the t. And then the last equality, again, we apply the definition of the moment generating function. Okay? As an illustration of this theorem, we have example 4.2.13. Okay, we have here x having a normal distribution with mean mu and variance sigma square. And then y also has a normal distribution with mean lambda and then variance tau square. And these are independent random variables. Okay, if we're going to now in exercise 2.3, I know you have encountered this in your undergrad probability theory, computing for the marginal, computing for the moment generating function of x, or in your reading assignment in chapter 3, reading assignment in chapter 3 regarding the normal distribution, we have computed for the moment generating function, because in the first part of chapter 3 we have the discrete distributions, and then in second section we have the continuous distributions. These two sections, given the probability density function or the probability mass function, we have computed for the moments, the mean, the variance, at the same time the moment generating function as a special expectation. Okay, so we have that as our moment generating function of x and y. And then using our theorem above, if we're going to determine the moment generating function of z, since it is equal to the product of these two moment generating function, then we have this. Okay, so by MGF technique, we can conclude that our random variable z has a normal distribution with mean, which is the sum of mu plus gamma, and then the variance is also the sum of sigma square plus tau square. Okay, so not only that we have found the moment generating function of z as the sum of these two random variables, but we also obtained the distribution of z. And then it's actually stated in theorem 4.2.14. So if we let x here as a normal distribution with mean mu and variance sigma square, y has a normal distribution with mean lambda, gamma, gamma rather, and then variance tau square, then b independent random variables, normal random variables. Then the random variable z, which is actually the product, no, not the product, but the sum of x and y, has a normal distribution with mean, which is the sum of the mean of x and y, and then the variance, which is also the sum of the variances of x and y. Okay? Okay, so hanggang dyan lang siguro ang discussion natin ngayong hapon. This is all for section 2 of chapter 4. So next meeting, I'm going to proceed now to section 3. Section 3 of chapter 4. And then,
Today.
Okay. Okay, and then section 4 of chapter 4, we have the hierarchical models and mixture distribution. I'm going to give you this section 4 of chapter 4 as a reading assignment. And then I'm going to proceed on chapter 5, not chapter 5, section 5 of chapter 4, covariance and correlation. And then the last section, we have the multivariate distributions. Since we started with the bivariate random vector, we're going to end on a multivariate random vectors in which we have a multivariate distribution. Okay, so this coming Thursday, I will be discussing section 3 of chapter 4. And then section 4, that will be a reading assignment. Okay, so to wrap it up, for section 2, we started with the conditional distributions, both for the discrete case and the continuous case. And after that, we discuss independence of two random variables. Then, the independence. Okay, so based on this premise that if we have random variables x and y independent, we can compute for the probability, considering that x and y are independent random variables. At the same time, we can also determine the moment generating functions of these random variables, as well as the random variable in which it is equal to the sum of the two random variables. Okay, so that's all for this afternoon. Siguro ako ni siyang i-send sa inyo ang PDF with the itong mga solutions na naisulat ko dito sa PDF. I'm going to send it. Attach na lang ako siya sa ang GC. So far, do you have any questions or clarifications with regards to this section? I want to remind you that our exam will be on September.
October 1, sir.
Dilday September. Yeah, October 1, Friday. Okay, Friday, October 1. The coverage for the exam, chapter 1 up to chapter 3. Okay, so that's all for this afternoon, and class dismissed. I'm going to stop now the recording.
Thank-
Bye, everyone.
Thank you, sir.